We are in Chapter 9, Inferences from Two Samples. Section 9.1 is Two Proportions. In Section 7.1 and 8.2, we discussed inferences regarding a single population parameter, proportion. The concept used in these previous sections will be extended to include two samples. So a hypothesis test, conduct a hypothesis test of a claim about two population proportions this time. And our confidence interval is going to be to construct a confidence interval estimate of the difference between the two population proportions. We have different methods for sampling. And the first one says, independent sampling method. When the individuals selected from one sample do not dictate which individuals will be selected in the second sample. And dependent sampling method, also called matched pairs sampling, is when the individuals selected to be in one sample are used to determine the individuals in the second sample. Note, it's possible for an individual to be matched up against him or herself. A lot of times you'll see it as where it's before an exam and after the course and going through it in a study guide, and then how they do on the post-test. Remember, there's a couple words to remember here. First one is qualitative data cannot be expressed as a number, and quantitative data is anything that can be expressed as a number. We also have a response variable, or a dependent variable, is the particular quantity that we are asking a question about in the study. Sampling distribution of a difference between two proportions, independent samples. Suppose a simple random sample of size N1 is taken from a population where X1 of the individuals have a certain characteristic, and a simple random sample of size N2 is independent and taken from a different population where X2 of the individuals have a specific characteristic. The sampling distribution, which is going to be P1 hat minus P2 hat, where P1 hat is X1 over N1 and P2 hat is X2 over N2, is approximately normal with a mean equal to P1 minus P2 and a standard deviation, and the formula is given, provided that NP is greater than or equal to 5 and N times Q is greater than or equal to 5 for both samples, and each sample size is no more than 5% of the population size. The standard version for our P1 hat minus P2 hat is then written as our Z, which is our test statistic, which has an approximate standard normal distribution. The null hypothesis is a statement of no difference. And this always means that for our null, we're going to have P1 is equal to P2. Because H naught is assumed to be true, that implies that P1 minus P2 is equal to 0, since they are equal. And we will also assume that P1 is equal to P2 is equal to P, and P is the population proportion. First example on here says determine whether the sampling is dependent or independent. Indicate whether the response variable is going to be qualitative or quantitative. So two different things to look at for these problems. So the first one says, a researcher wishes to determine the effects of alcohol on people's reaction times on a stimulus. She randomly divides 100 people aged 21 years old or older into two groups. Group 1 is asked to drink 3 ounces of alcohol, while Group 2 drinks a placebo. Remember, a placebo is something that looks and smells and tastes just like alcohol. However, it's something just like water. It has no alcohol in it. Both drinks taste the same, so the individuals in the study don't know which group they belong to. 30 minutes after consuming the drink, the subjects in each group perform a series of tests meant to measure reaction time. So first question, it says, determine whether the sampling is dependent or independent. Since we're dealing with people, and all they did was randomly put these 100 people into two groups, this is going to be independent. The second question asks for indicate whether the response variable is qualitative or quantitative. And since we are measuring reaction time, this is going to be quantitative. Part B says a political scientist wants to know how a random sample twins over 18 years old feel about the Democrats in Congress? Really quick, it does say twins. She obtains a random sample of 224 registered voters who are also twins and asks, do you have favorable or unfavorable, rotating that, opinion of the Democratic Party? Each individual is asked to disclose his or her opinion about the party, and the twins' opinions were recorded. So, first question, is the sampling dependent or independent? Well, since we're dealing with twins, if I select one student or one person that's a registered voter and to survey them, I have to select their twin. So that's dictating who I have to select for my second group. So this is an example of a dependent sampling method. Second question is asking for, is the response variable qualitative or quantitative? And since they're asking for their opinions, that is not numerical, and this is going to be qualitative. So the next thing, the box, give that a star. This is hypothesis test regarding the difference between two population proportions with an TI-83 or 84 calculator. To test the hypothesis regarding two population proportions, P1 and P2, we can use the steps provided that, so these are what we have to check. First thing is simple random samples for both of those. The two samples are independent, big one there. And n times p and n times 2 are greater than or equal to 5 for both samples, so a lot to check. Step 1, determine your null and alternative hypotheses. So if you look at your null, it's the same for all of them. It's P1 is equal to P2. And your alternative is either a two-tailed, left-tailed, or right-tailed test, and that dictates the symbol that's going to go in there. Step 2 says to select alpha. Again, that's normally given to you guys in the problem. Step 3, we're going to go stat test number 6, which is 2 prop z test. We're going to enter the values x1, n1, x2, and n2. Be careful not to mix those up. Select the appropriate relation between P1 and P2 and calculate. We'll give you, there's two out things that we need to really look at. Z, which is our z-score, which is our test statistic, and p, which is our p-value. If the p-value is less than alpha, we reject our null, and the last step would be to state our conclusion. So we can also consider a confidence interval estimator of the difference between the population proportion P1 minus P2. If the confidence interval estimate of P1 minus P2 does not include 0, we have evidence suggesting that P1 and P2 have different values. Consequently, a conclusion based on confidence intervals might be different than the conclusion with the hypothesis test. Confidence intervals are always needed to be set up as a two-tailed test, and that's really crucial. We want to make sure that we talked about that before, but definitely a big part to know. So highlight that. Confidence intervals are always, they need to be set up as a two-tailed test, because remember, confidence is that middle part. There's always things on each end that we're not confident with. So to conduct a test using confidence intervals, find confidence intervals, and then are two things that we need to know. First one is if 0 is in the confidence interval, then we do not reject the null. And if 0 is not in the confidence interval, then we reject our null hypothesis. So the next step on here, give this box a star, is constructing a confidence interval for the differences between two population proportions. This is again for independent samples with an 83 or 84 calculator. To construct the confidence intervals, we need to again check to make sure that all the criteria has been met. Step 1, we are going to go to stats, test to 2 prop z int. Again, enter in all of your information, x1, n1, x2, n2. Enter your confidence level. And remember again for this, it always needs to be a two-tailed test. So just keep that in mind when we set these up. Calculator is going to give you your lower bound and your upper bound, and then from here you need to interpret your result, which is going to be looking at what we have up here with those two different scenarios, if 0 is included in the interval and 0 is not included in the interval. So the next example we have says test whether P1 is less than P2 at the alpha equals 0.05 level of significance. Sample data is given, and x1 is 109, n1 is 475, X2 is 78, and N2 is 325. Assume that the samples are obtained independently using simple random samples. So we have some parts on here. The first part is asking us to determine our null and alternative hypotheses. So let's go ahead and write down H0 and H1. And we were given up above that this is what we are testing. So this is our alternative. And so our null is always going to be that they are equal. Step 2, or part B, says determine the test statistic. On your calculator, you're going to go to Stat, to Test, and down to Prop Z test. And then we need to enter in our values for X1, N1, X2, and N2. So X1 is 109, N1 is 475, X2 is 78, and N2 is 325. Your alternative hypothesis is less than, and then go down to Calculate. Select Enter, and you will get your Z, which is your test statistic, and P, which is your p-value. From the calculator, we get our test statistic, which is going to be Z equals negative 0.35. Part C says determine the p-value and conduct the test. So we saw earlier that the p-value on our calculator is equal to 0.3649, which is greater than alpha, which in this problem is equal to 0.05. And from this means that we do not reject H0. I'm going to go ahead and write a star here and have you guys write your own conclusion, and then we'll talk about it in class. Part D says to construct a confidence interval appropriate for the hypothesis test. And so we have a left tail test up above. And since we have a left tail test, that means that alpha is equal to 0.05 is going to be over here in the left tail test. But again, remember for confidence intervals, we need to set this up as a two-tail test. So go ahead and put another tail over there on the right. And this tail, because we have a symmetric curve, is also going to be alpha, which is equal to 0.05. And so since we have alpha is equal to 0.05 twice, that means that the leftover part is going to be in the middle, which is 0.90. And so from this, that means that our C level is going to be equal to 0.90. So from the calculator, we have a lower bound of negative 0.061 and an upper bound of 0.040. And so from here you need to ask yourself if 0 is in this interval. 0 is in the interval. And what does that mean? So if we go back up, so this says if 0 is in the confidence interval, then we do not reject the null hypothesis. So 0 is in the interval, which means do not reject H0. And looking at this conclusion that we had for part D, which is using the confidence interval approach, that matches what we had up here in part C, which was using the p-value approach. So two different approaches to figuring out if we reject or do not reject our null hypothesis. The next example says, a study was conducted to determine the proportion of people who dream in black and white instead of color. Among 306 people over the age of 55, 68 dream in black and white, and among 298 people under the age of 25, 13 dream in black and white. Based on data from, and the studies stated there, says we want to use the 0.01 level of significance to test the claim that the proportion of people over 55 who dream in black and white is greater than the proportion of those under 25. Test the claim using the hypothesis test is part A, and part B says test the claim constructing an appropriate confidence interval. So first thing we need to do from this problem is talk about this and ask what is our parameter that we are using in this problem. And we're talking about proportions, and it says that in the problem. So we know that our parameter is going to be proportions. We also realize that there's two groups here, and we have people that are under the age of 25 and people that are over the age of 55. And those people are independent of one another. So this is independent sampling. And what was nice with the last problem is I was very cut and dry with what X1, N1, X2, and N2 are. And this one isn't. It's written in paragraph form. This is more like what you guys will be seeing. So we're going to kind of make a table to kind of organize our numbers just so we don't make a mistake with entering them in. So let's go ahead and do that first, and then we'll write down our null and our alternative. So the first thing is we have two groups, like we said. And we're going to call group 1, I'll say P1, is going to be over 55. And then we're going to have our proportion 2, which is going to be under 25. And from each of these, I need to have an X value and an N value. And so over 55, we had 68 that dreamt in black and white out of 306. And for those that were under 25, 13 dreamt in black and white. And we studied 298 people under the age of 25. So this is kind of an organization way to kind of make sure you put the numbers in correctly on your calculator. A lot to read and a lot to take in. So first thing is going to be we need to write down our null and our alternative hypotheses. So H0 and H1. So the null is always going to be that those two proportions are going to be equal to one another. In our alternative, we need to look at this. And the wording on here is that the proportion of people over 55 who dream in black and white is greater than the proportion of those under 25. So the symbol, if you want to think of it that way, that would go in here would have been a greater than. And so for this problem, we need to have P1 is greater than P2. Now we need to use our calculator and put all this data in and get a p-value. On your calculator, you're going to go to Stat, Test, to Prop Z Test. And from here we need to enter in our values. We have X1, which is 68, N1, which is 306, X2, which is 13, and N2, which is 298. Our alternative hypothesis is greater than. Select Enter. Go down to Calculate. We get Z, which is our test statistic, and P, which is our p-value. Be careful because it does have an e to the negative 11th in there. From the calculator, we get a p-value equal to 6.01 times 10 to the negative 11th, which is going to round 4 decimal places to just 0, which is less than alpha, which is equal to 0.01, which means that we are going to reject H0. So from here we need to write a conclusion. So in conclusion, there is sufficient evidence at the alpha equals 0.01 level of significance to conclude that the proportion of people over the age of 55 who dream in black and white is greater than those who are under the age of 25. So the next part says, for part B, says to test the claim by constructing an appropriate confidence interval. So again, we're going to draw our normal curve. And for this test, we are dealing with a right tail test. And so our right tail is going to be equal to alpha, and alpha is going to be equal to 0.01. And so alpha is equal to 0.01. On the other side, also on the left tail, because of, again, it being symmetric, so that means 1 minus 0.01 minus 0.01 is going to be left over with the middle, which is 0.98. And so that's going to be our sea level, is going to be equal to 0.98. So from the calculator, we get a lower bound of 0.117, comma, 0.240. And 0 is not in this interval. So from page 2, we see that if 0 is not in the confidence interval, then we reject the null hypothesis. So since 0 is not in the interval, this means that we are going to reject H naught. The conclusion would be the same thing that is also written up above in part A. So C says, an explanation given for the results of those over the age of 55 grew up exposed to media that was more displayed in black and white. Can the results from part A and B be used to verify this explanation? And no, remember that we have, just because something has some kind of relationship between it, we cannot prove that there's any kind of association between any logic behind this. We're just running a test, and further exploration would have to be done in order to figure out the reasons why.